video, we are going to continue talking about the components of optical spectroscopy instrumentation. Before we jump into today's topics, I would like to do a little bit of review from last video. And really, it's just remembering which components are common, which types of components are common in those instruments. And so the first is a source. The second is a wavelength selector. And of course, you know, the order of these last few can differ depending on the type of measurement that you're trying to make. The third is the sample cell, or the sample holder. The fourth is a detector of some sort. And then the fifth is some sort of readout transducer signal processor, right? Something that will change your signal from current or voltage into a number that you can interpret and use in your analysis. All right, so keeping that in mind, let's look at what we're trying to do this video. So we're going to do a little bit of theory behind continuum sources. So we talked a lot about deuterium and xenon arc lamps as continuum sources last video, but we're going to go back and think a little bit more about blackbody radiators and in particular, a glow bar that's common in IR spectroscopy instruments. We're going to talk about types of lasers. So we went pretty deep into theory here last time. We're going to talk about what kinds are available and why you might choose one over another. Then we're going to jump in and talk about the rest of the components that we need to for an optical spectroscopy instrument, right? From that list of 5 we just made. So sample cells, wavelength selectors, and detectors. And we'll talk about theory and types for each of those. All right, so as I said, we're going to revisit some sources. So last time we hit deuterium lamps and xenon arc lamps. This time I want you to think about a glow bar, which is a silicon carbide literally bar, I'll show you a picture, that heats up, and when it hits a certain temperature, right, it starts to emit light. This is the same sort of phenomena that if you have an electric coil stove, you see this at your house every day, or however often you use your stove. So let's talk a little bit about theory of how this works. All right, so blackbody radiation is a kind of radiation that is emitted. So what we think about when we're talking about blackbody emitters is we're looking at the light that these blackbody emitters put out as a function of temperature, right? So think back to your physics courses and think, and remember that blackbody, that term, is really a description of a container or object that absorbs all radiant energy that's incident upon it. And it's in thermal equilibrium with its environment, so it emits as much energy as it absorbs. And so the energy emitted in the form of heat and light, we're really concerned about the light part right here for spectroscopy. So the energy emitted in the form of light, and that's the spectral distribution of that light, shifts to shorter wavelengths as the black body surface temp increases. So that's depicted over here on the right. This is an example of Wien's displacement law. And we'll talk about that in a minute. But I want you to remember that blackbody, the emission of light from a blackbody was first described by Planck's radiation law, which, if you remember, looks something like this. So you have the spectral radiance of that black body as a function of wavelength, described by 2h times the speed of light squared over the wavelength to the 5th, multiplied by 1 over e to the positive hc over lambda t, multiplied by Boltzmann's distribution, or Boltzmann's constant, minus 1. All right, so hopefully this rings a bell for you. Basically, the reason we're interested in knowing how we could calculate the spectral radiance of any particular blackbody radiation source is because for any particular source, right, we can now find the maximum wavelength of emission, of emittance as a function of temperature, right? So as a function of temperature, I can find a wavelength of emission. Okay, this is great. This is great news. So in order to explain the curvature of this sort of temperature dependence on the spectral distribution of the radiation coming from a black body source like a glow bar, we use, like I said, Wien's displacement. So turns out that we can derive an expression for the emitted wavelength with respect to temperature. And so the way to do this, right, is to derive Planck's radiation law. 2hc squared over lambda to the fifth multiplied by 1 over E hc. Don't mind me talking to myself as I write this out. Okay, so we can derive this, take the derivative of this equation with respect to wavelength and then set it equal to 0. So I want you to think about that for a minute. Do you agree? I think we could get there, and then we'll do a little bit of a simplification. And when we do that, and I'll spare you the calculus, the wavelength of maximum emittance is equal to 2.897 times 10 to the 6th over the temperature. So I said that I could derive the wavelength of maximum emission just as a function of temperature, and I did that by taking the derivative of Planck's radiation law and setting that derivative equal to 0. All right, so in this function, wavelength is in the unit of nanometers and temperature is in the unit of Kelvin. So in this question below, I'm asking you to consider that electric stove coil that you might have in your house, assuming it's a perfect black body. What is the temperature when it's on, of the coil when it's high, meaning like a color of orange, and low when it's like red? And so I could calculate this. T equal to 2.897 times 10 to the 6th over 650 nanometers would be something like, I'll let you calculate that number, right? And I could set up the other exactly the same way, 2.897 times 10 to the 6th over 750, right? So I should get something like 4460. This one, 3860. Cool. Okay, so useful. We can also manipulate Planck's radiation law to calculate the total emittance of a black body, and so the total brightness. And to do that, we just integrate Planck's original description of a black body across all wavelengths, which makes good sense. So the total emittance of your black body is given by the integral from 0 to infinity wavelengths of that original function. That's a function of wavelength. And if I do that, and I do that integral and I simplify, what I end up with is, oops, no, that's not gonna work. This very simple equation. So the Stefan-Boltzmann's constant which is equal to 1.8047 times 10 to the minus 12 watts per centimeter squared per Kelvin to the 4th. Okay. Multiplied by the temperature. So it's a function of temperature again, which shouldn't hopefully be surprising to you. So turns out that it's pretty hard to have a complete black body in practically as a radiation source in an instrument. And so really what we're talking about using in instruments are gray bodies. So gray bodies are non-ideal black bodies that approach actual conditions of black bodies, but they're not quite perfect. And so the way that we can get at the spectral emittance of a gray body, so notice I don't have the superscript B, that's indicating that it's not a black body, but a gray body. And I can do this by using a couple of modification factors. So I'm going to modify the ideal black body. So the two modification factors are sort of defined below, but I've got epsilon as a function of wavelength and T sub W. So epsilon is a function of wavelength as the spectral emissivity of the source, right? So the table on the right, table 13.1 from Optics by Hecht, gives an idea of some representative values. So anything that is reflective or it otherwise does not readily absorb light has a really low spectral emissivity. Anything that absorbs that can absorb radiation is pretty well is given a number closer to 1. Because this is a ratio, you should never have anything greater than 1, right? But this is a way to correct for the amount of radiation that this ideal black body can actually take in when it's a gray body, right? The next variable that we have to keep in mind is the transmission factor of the source envelope. So, I should mention one other thing. This spectral emissivity, right? It's a function of wavelength. So it's specific to a particular wavelength. So this number can change as wavelength changes. All right. So T sub W is the transmission factor of a source envelope. So I want you to think about, generally speaking, let's call it sort of a light bulb. Okay. So here's your light bulb, and here's the filament that goes through your light bulb. So the filament in this case is the source, right? That's the thing that gives off the light, and the glass around it is the envelope. So the transmission factor of the source envelope is meaning how much of the light that's given off by the source is actually reflected or absorbed at this glass surface of this source. And so this is a thing that can be measured. So if I go to the next slide, I can describe a real continuum source using these terms, right? So the steps by which I might do this, I'm going to identify the spectral radiance of my real source and adjust the temperature in Planck's radiation law for an ideal black body in the x direction so that the peaks of the spectral radiance line up to the spectral radiance of the gray body. So let me go back, right? Meaning here, I'm going to measure the spectral radiance of my gray body. Then I might have to choose, maybe not the same color. I'm going to find the one. So once I have an empirical spectrum, I can use the theoretical spectrum for that, for the way that should behave if it were a true black body. And I might have to adjust, right? Because remember, Wien's displacement law says that the temperature affects the maximum wavelength of emission. And so I might have to, using temperature, adjust one way or another, right? So if my maximum emission of my gray body was right here, and my black body says it's supposed to be way over here, I can adjust using a change in temperature. So that's what this first step is really getting at. So that adjusted temperature is what we call the color temperature. So then I can take the ratio, not the radio, the ratio of spectral radiance of the gray body to the black body, and that is equal to the product of the spectral emissivity and the transmission factor, which should make sense because we said that the total spectral emittance of the gray body was equal to the black body multiplied by the emissivity multiplied by the transmission window. And so if I have the ratio here, oops, nope. All of a sudden, it makes sense that I have the ratio equal to the products, right? Then I can measure the transmission factor in order to calculate the spectral radiance of that gray body. All right, so I can mathematically describe a gray body's emission spectrum. So a little bit of theory to get you going this morning on continuum sources. All right, the next thing I want to jump into is the kinds of lasers that are available to you. So we talked about these. We talked about laser theory a little bit last video, but let's revisit just briefly. We said that lasing is possible via stimulated emission, which was a way to sort of increase the total number of emitted photons of a particular wavelength. We could do this if we could pump the lasing medium to increase the total number of electronically excited atoms so that they were greater in number than the electronic ground, or atoms of electronic ground. And so we're going to go through stimulated absorption. Hopefully, if we had enough of a population inversion, we would not have spontaneous emission, but instead have stimulated emission. All right, so hopefully that's a quick review. This idea of population inversion is theoretically hard to do unless you have broken down your, or you have available to you a secondary energy level that in this diagram we called E sub x, where once we pump our active medium to increase to excite the medium itself, right, whether it be ions, atoms, molecules, you'll have a fast non-radiative decay to this slightly less energetic metastable energy level. In this diagram we call it E sub x, and this is where you have that population growth in order to achieve population inversion. So at this point you're going to hit the electronically excited but metastable lasing medium with light that is equivalent to with light that has intensity equivalent to E sub x minus E sub 0 in this diagram, and to actually get your laser to laze. So in the image to the right, remember, so in the first window, we have one quanta that can trigger an in-phase emission of another, right? Here we're dumping, then the second panel, we're dumping energy from the metastable state into that growing wave. So from the metastable state into the growing wave of photons. And then here in the third panel, the wave grows as it sweeps back and forth. Remember, because we have two mirrors on either side, one of which can be transmissive. That's why you have a little bit of light coming out of that active lasing medium. As long as we can overcome the loss at this end with this semi-transparent mirror, we can have a continuous laser. All right, so here's an example of a ruby laser. So a ruby is a solid state laser, and one of the first lasers described. And specifically, the active lasing medium is an Al2CO3 substrate, and in it there's a small impurity of chromium, so C2O3. And so this is where you can get that excitation happening of that chromium. So remember, we said that we were going to pump we were going to optically pump our active lasing medium by shining light on it, right? That's how we get that initial excitation into E1 or EI. Then hopefully we can achieve population inversion because of the identity of the lasing medium and the electronically metastable state that is EX. So as we pump this active lasing medium, we're going to achieve population inversion, which is excellent because then we can get stimulated emission. That stimulated emission is going to result in a coherent parallel wave that bounces back and forth between between these two mirrors. Okay. And occasionally, or at some consistent low level, you'll have transmissivity of this wave through this partially transmittive mirror. So exciting stuff. So let's kind of take this diagram and apply it to this laser. So here is our flash lamp. This is how we optically pump our ruby laser. We have a fully reflective mirror right here, okay, a partially reflective mirror here, and this is our ruby amplifier rod. So notice how we are optically pumping our ruby active medium, and with our fully reflective and partially reflective mirror, hopefully we'll end up with lasing if we can achieve population inversion via that flash lamp. Okay, hopefully that helps as a little bit of a review. So now I want to talk about sort of laser characteristics. What do we need to know when we're looking at lasers for inclusion in particular instruments? And the first thing you should know is the state of matter, right? Is it gas? Is it a dye laser? Is it an ionic laser? Gotta know what it is. That'll matter. We'll talk about why in just a minute. The next is, how is it pumped? Is it optically pumped? Right, that's pretty common. Thermally is possible, though less common. Yeah, we'll leave the list there. You can use a second laser to pump your first laser if you really wanted to. You don't have to use something like a flash lamp that's a continuum source, so it gets complicated, or it gets diverse. There's a lot of different ways to do that. And then the last question you have to ask yourself is, will your laser have a continuous wave or will it be pulsed? So a continuous wave is, right, the consistent, constant number of photons that make it through your transmissive mirror at a time. So over time. So if you have time across the x-axis here, an intensity of light emitted on the y, a constant wave laser would have a constant amount of intensity being emitted from it. The other option you have is for a pulsed laser. So you have discrete packets of photons that are emitted on a frequency that you can choose usually. So it would look something like this. Right? Over time, you would have really discrete but high power, high intensity packets of photons that are being emitted by your laser. So let's talk about it. So solid state lasers are great. They have strong power output. They're usually crystals or glass that's doped with rare earth metals, right? So that's the example of the ruby that we talked about earlier. They are usually pumped using some sort of optical source, so either a flash lamp, a laser diode, or some other laser, depending on which one you're thinking about. Because of their strong power output, they're generally used in research. Laser ablation, right, would be some sort of destruction of a particular substrate to get that substrate to be in a different phase, something like An example would be if you're familiar with MALDI, right? If you're going to try to do mass spec on large molecules, and you need to get those molecules into the gas phase from the solid state, you could use a laser in order to make that happen. Okay. Yeah, so these are common. They're generally not super expensive. They've been around for a long time. If you're looking for gas, there are so many. This is a partial list. A neutral atom Heine laser is probably the most common in spectroscopy research, mostly because it's low cost, reliability, has high reliability, and low power consumption. It works on an electrical discharge to pump. It's often used in spectroscopy research, and it's generally a continuous wave, which is helpful. There are lots of other examples. The usefulness of each is, specific. If you might use an ion laser to pump another laser, you might use it in a lithography application. The realistic usefulness here is it's low cost, it's reliable, and it uses low power. To do that, probably the usefulness there is because you're not using any sort of optical pumping. So a lot of these are useful and can be applied in many instruments. Another example is a dye laser. So these are nice because they're continuously tunable. So the knock on a laser, right, is that it has a pretty narrow wavelength, or set of wavelengths even, that it can actually output. The nice thing about a dye laser is that it's continuously tunable in the UV vis, and that's accomplished by replacing a non-transmitting mirror with a reflective grating. So we'll talk more about wavelength selectors in a little while, but basically it reflects a narrow band of radiation that you can select. And the way that you even get more than one wavelength of light from a dye laser. So I'm going to draw a diagram here. So here's NO, or sorry, not N. I'll use E for consistency's sake. So here's my energy level 0. Here's my excited energy level, first one. Here's E sub X, as we talked about before. So in a dye laser, you're actually thinking about 4 levels. So I'm going to call this E sub Y. Okay. So instead of a 3-level laser, you're talking about a 4-level laser. And so you're going to optically, or probably optically, pump your dye laser. So then you have that fast non-radiative decay to this metastable state again, right? That's still the same. The cool thing about a dye laser is that because you're using a molecule that has sort of lots of ways to arrange electrons in its molecular orbitals, you have lots of different spots that these in terms of energy, that these metastable molecules can sort of relax back down to. So it could relax to here, could relax to here, could relax to here, could relax to here, right? And it's all of these are different. So these E levels that we're talking about are electronic excited states, but these smaller levels here are vibrational. And if I really wanted to zoom in, I could zoom into rotational levels. And so because there's such a variety of wavelengths that can be emitted in order for those molecules to relax back down to ground, you have a really wide range of wavelengths that are possible to be emitted. And that's how you can have such a variety to choose from using your wavelength selector. It's also kind of nice because a 4-level laser makes it easier for you to achieve that population inversion that's required for lasing to happen in general, right? So if we're thinking about it, population inversion in its most basic sense says that you have to have more excited than molecules or ions or atoms than you have non-excited. And so if I'm doing that comparison across just E naught and E1, that comparison is hard to achieve because you have to get this pumping to work really efficiently, right? It has to be really fast and it has to work every time, right? The efficiency has to be high. If you're thinking about it this way, where you have a 3-level laser, that it makes it easier, right? Because then you're comparing, instead of comparing E0 to E1, you're comparing it to EX. And because this is metastable up here, you can grow the population much more easily than if you were stuck in E1. The usefulness of EY here is this transition happens really quickly. Okay, so that means that because this is metastable and things come down from here really fast, there's almost always nothing here and there's almost always lots here. And so population inversion is much easier to achieve using a 4-level laser than a 3-level laser. So dye lasers are kind of cool in that way. If you're interested, here's a paper from Zhu who talks about fiber-based tunable microcavity fluidic dye lasers. So in this example, he's using rhodium 6G as a dye. He's optically pumping that active lasing medium, that dye, in a capillary using a 532 nanometer pump laser. And he's using a translational stage to get the laser output tuned to where he wants it to be, which is kind of cool. All right. Other examples are things like semiconductor lasers. So these are diodes, right? So population inversion occurs in a semiconductor when high electric fields applied across a p-n junction. So in this case, you're looking at your electrons hitting holes, which can turn into wavelengths of emitted light photons, right? All right, semiconductor lasers are fine, but we'll continue. All right, so we talked about continuum sources, we talked about some lasers. Now we need to talk about the rest of these components. And so sample containers is the first one. I am not going to do anything else except for to say there are 2 things that you should think about as you're choosing a sample container. The first one is that it has to be transparent to radiation, so the material that it's made out of should matter. The second thing is that the geometry of that sample cell should minimize signal scatter. So for example, a square cuvette is square because it minimizes the scatter of light as it passes through. If you had something, right, so you have some loss due to reflection off of sort of a non-parallel beam hitting your glass window, but most of it makes it through, right? If you had a circular cuvette, you may not have that luxury, right? So you'll have much more chance for internal reflection in this example than you would in a square. Because, right, we're talking about practicalities here. So the likelihood that you could get this guy into the instrument in a perfectly, with the optical path perfectly parallel is small compared to whether or not you can get this really wide flat window set in the right spot in your instrument. All right. So those are the 2 things you should keep in mind as you're thinking about sample cell containers. The next thing we need to talk about are wavelength selectors, and we're going to talk about 2 major kinds. So wavelength selectors are critical in optical spectroscopy, mostly because we require in those measurements that radiation consists of a small, narrow, continuous group of wavelengths that we call band. In order to obtain that kind of radiation, we use these wavelength selectors. And so there are a couple of different kinds. We're going to focus on two. The first one we're going to talk about are different kinds of filters, and then we're going to talk about monochromators. There are many, many others. And I recommend that you take a look at those in your text, the undergraduate instrumental analysis text from Robinson, but I won't go into those here for the sake of brevity. Okay, so ideally, in a wavelength selector, you want three main qualities. You want to pass a narrow, limited band of wavelengths. So look at this plot over on the right. We're talking about percent transmittance of light through an optical filter. Okay, so we want this band to be, so our first criteria is that we want a narrow band of transmitted light. Okay. So without a scale on this image, it's hard to say whether or not this one is actually narrow, but basically you're going to say that you only want a very narrow band of light transmitted. Okay. We want a sharp cutoff and a high percent transmittance. So actually, let me go back. The way that we actually quantify the width of a band of transmittance is to look at the effective bandwidth. So the effective bandwidth is an inverse measure of the quality of the device. A narrower bandwidth represents a better, more specific wavelength selector. So to do that, we look at the full width of the peak of transmittance at half the maximum transmittance. And so if I'm at, maybe we'll call this 75. No, let's call it, for ease, let's call it 80. 80% total transmittance of the light that comes through at the nominal wavelength maxima. So that means that the full width of that peak at half max, which would be 40% transmittance, is where I will sort of measure this width. And that's a quality characteristic that you'll find as you're looking for wavelength selector filter characteristics in your first assignment this week. Okay, so we want this number to be small. All right, so the next thing is a high percent transmittance. So in this case, at max, you're going to get 80% transmittance of the light at the maximum of this peak. Okay. The other thought is we're going to talk about cut on and cut off, or low pass, high pass, dichroic filters. The other thought here, right, is that the cutoff should be sharp. This is sort of another way to get at this first point, right? You want this band to be narrow. The other characteristic that's desirable, it's always desirable, is low cost, right? That's not always achievable, but sometimes it is. All right, so let's go on and talk about what types of filters are available to us. So the first one that I want to talk about is an absorption filter. So these are useful in the visible range of electromagnetic radiation. They're less expensive. That checks the box for 0.3 on the previous slide, but they're usually less selective. So they have large full width, half max effective bandwidths. So in general, they're made of a colored glass sandwiched between two glass plates. They have effective bandwidths between 30 and 250 nanometers. So this distance is between 30 and 250 nanometers, right? That's a pretty wide range to be considered, right, a filter of any sort. And unfortunately, the peak transmission is about 10% for a fairly narrow bandwidth filter. So if I'm erring on the side of narrow, I'm going to reduce the transmission efficiency, which is usually not desirable. However, if you need a low cost option and you have a high intensity powered source, this might be for you. And so you can combine multiple filters in order to sort of select a particular wavelength of interest to you. So in this image to the right, you see a green filter here, and it passes about, I don't know, 540 nanometers of light. That's where the transmission maximum is. You could also pair it with an orange cutoff filter, okay, so that this filter in particular will cut off any sort of transmittance with higher wavelengths than that orange color. And so the idea here is that you'll have, if you combine these two, something that looks like this, right? Okay, so you can combine these in any sort of way that works for you. Notice that again, the total percent transmittance is relatively low because you're taking these two, which are low to begin with, and adding them together, which makes this combination even lower, right? That percent transmittance efficiency in that realm is additively bad in this case. All right, so the next one that I want to talk about is probably the one that's most common. And so it's called an interference or a dichroic filter. Here, what we're doing is relying on optical interference to transmit a narrow bandwidth of light that is incident upon this filter. And so I'm going to draw some scenarios that are happening in sequence. Okay, so first things first, you're going to have collimated light. So let's talk about the structure of this filter first. So if I'm over on the right-hand side of this slide, notice that I have a glass plate that is sandwiches a metal film, a dielectric layer, and then another glass plate, or sorry, metal film, and then a glass plate. And so basically what's going to happen is you're going to have polychromatic radiation hitting one side of this filter, and that optical interference is going to, that happens sort of in the middle of this sandwich, is going to result in a narrow band of radiation coming out the other side. Okay, so let's talk about how that happens. In particular, right, you have, let me label these. So this is my glass plate, here's my metal film, here's my dielectric, here's my metal film, and my glass plate. Let's assume my white light is coming from this direction. So I have collimated light that is partially reflected at that first metal layer. I'm coming in through glass. Some will be reflected back out at the outside of this first metal layer. Some will go through. Okay, this is a thin metal film. If the light goes through the first metallic layer, it bounces off and is reinforced by the, let me back up. So it bounces off the inside of the next metal film. Okay, goes through the dielectric, which is usually MgF2, occasionally calcium. Okay. It goes through the dielectric and it bounces off the inside of that second metal film. Okay, so something like this. It'll bounce off the inside of the first metal film. And this, so as more collimated light is coming through and being transmitted through that first metal film after some is bounced back, you're going to have reinforcement of a particular wavelength of light based on the thickness of this and identity of this dielectric layer. Okay, so particular wavelengths of light are going to be reinforced while others are going to be sort of bounced backwards and out. So we have destructive interference of all of those other wavelengths that aren't the wavelength that's being reinforced. Okay, so what happens is you have transmittance through that second metal film, and then eventually through that glass plate. All right, so as I mentioned, by controlling the identity, the identity and the thickness of the dielectric layer, you can control the wavelength that's selected through this constructive interference process, okay? Okay. The other part that I wanted to mention is that you can actually calculate the wavelength of that's selected via constructive interference if you know the thickness of that dielectric and the order of interference that is prevalent in your glass plates. So let me give you an equation. So the wavelength transmitted is equal to 2 times the depth of the dielectric multiplied by the refractive index, right? That's why the identity matters, because refractive index will change over the order of interference. So I'm giving this a bold small n. That's what this will end up being, right? A bold small n. So D is the depth of the dielectric. Non-bold n is the refractive index. Oops. Of the dielectric, and then bold n is the order of interference. So think back to physics. Yeah, I think I'll leave it there. If you have any questions about this, you can shoot me an email. All right. So practical uses of interference filters. So there are 4 main uses of interference filters that are common in optical spectroscopy instruments. So all of these plots have percent transmitted plotted as a function of wavelength. So in the first one, I'm going to show you this shape. We call this a long pass or a cut-on filter. So I think it makes plenty of sense to say that these longer wavelengths out here have high transmittance. So long wavelengths are passing, right? So we call this a long pass filter. You can think that there's probably an opposite of that, or we call it a short pass or a cut off filter. Another example, a band pass, right? Where we have a really narrow specific band of light that will actually make it through that dichroic. And then the opposite of that, I think, right, is called a notch. That seems pretty obvious, is a notch filter. This one, band pass and a notch filter. So here, this is useful if we're trying to get rid of a specific wavelength of light, maybe from a laser, to reduce noise because of a super intense radiation source. All right, so those are the practical uses of those interference filters. The next type of wavelength selector that we should consider are monochromators, and this is a really commonly used wavelength selector. We'll talk about some particular modifications that you can make to change up this setup, but in general, the way a monochromator works is that it disperses polychromatic light in order to select a narrow bandwidth. And this is nice because rather than having a fixed bandwidth, monochromators can vary the bandwidth of light selected in real time, right? So these are pretty useful. So normally this optical setup that we're going to talk about in just a second is housed in some sort of black box to eliminate the effects of stray light Okay. First component is the entrance slit. Okay, so here at the entrance slit, you have the production of a rectangular optical image. Okay, so consider that for a minute. Probably polychromatic light, right? So in this example, I have two wavelength. This set of polychromatic radiation is made up of two wavelengths. So lambda sub 1 and lambda sub 2. So I have lambda sub 1, lambda sub 2. The idea as this polychromatic radiation goes in through the entrance slit, I have a rectangular optical image. The next element that your light will encounter is a collimating mirror. So the idea here is that we're going to produce a parallel beam of radiation. Right, notice that the effect of light coming in through a slit is that you have this sort of dispersion of your radiation. The idea of this collimating mirror is to collect that dispersive radiation and produce a parallel beam. Okay. The next thing that you would like to that your light will encounter is a grating. So that's this guy here. So the idea of a grating is that it actually disperses the radiation into component wavelengths, right? So I said that we had two wavelengths in this polychromatic radiation that was coming into this monochromator. And so this is where the separation of those two wavelengths happens, right? So if a monochromator's purpose is to separate polychromatic light in order to select a narrow bandwidth of light to exit that monochromator, this is the part of the monochromator that actually does that selection. All right, we're going to talk more about how this works to select wavelengths of light in the next slide, but we're going to continue on sort of our general survey of what a monochromator is made up of. The next component is a focusing mirror. So a focusing mirror is really handy. So I'll give you a number here. 1, 2, 3, 4. So a focusing mirror is really handy. It's going to take the collimated light coming from the reflection, the grating, in this case it's a reflective grating, and it's going to form an optical image that focuses on the planar surface of our, at the focal plane of our monochromator, right at the exit slit. So it reforms the optical image, and focuses it on the planar surface at the exit, which ideally should be at the focal plane. So the idea here is that we are focusing this light into a single image, optical image. All right. The last is, of course, the exit slit. Here, the exit slit is just a rectangular hole that occurs at the focal plane that isolates the desired wavelength. Okay, so because the focusing mirror is collecting all of the light of a particular wavelength at the focal plane, at a particular point on that focal plane, you can imagine, right, that if I moved this focusing mirror, if I just rotated it, keeping the center point immobile, I could sort of move this point wavelength across the focal plane so that if I wanted to only select the second wavelength, I could move this mirror to select only this guy coming through this slit, right? And so the exit slit is useful because it isolates or only allows through our particular wavelength of interest. All right, so let's talk more about gratings. So gratings come in lots of different flavors. So this is an example of a blazed grating, this image down here on the left. Basically, we have a plane or a concave plate that are ruled with loosely spaced grooves. So this is the same idea that you'd find on like a CD or a DVD, right? You just have really narrow grooves of light, narrow grooves into the surface of that CD, and that's how you reflect back a rainbow, or those blazed lines. And so basically, different wavelengths are diffracted and constructively interfere with a maximum at this beta, when beta is, of course, not defined on this slide. It's the angle of maximum constructive interference. And it's measured against normal. So let's define where normal is on here. Oh, it's already defined, good. Grating normal is perpendicular to the surface of the grating. So beta is this angle of maximum diffraction. So if you have an incident ray coming in here with an angle alpha, it will be diffracted at an angle beta, right? That's how that works. The idea here is that these grooves in this example of this plane grating is that these grooves are blazed at an angle that concentrates radiation in a particular direction. So rather than having it bounce directly back at the same angle as the incident ray, the idea is you will be able to concentrate that particular wavelength of radiation in a particular direction, which is useful if you think about the design of our monochromator, right? We'd want it to go into a particular direction, so it hits at this focusing mirror at a particular spot. Okay, so we can think about Bragg's law, okay, in defining the relationship between the incident angle, the diffraction angle, and the wavelength of light that's being incident upon this blaze, or upon this grating. So D is the groove spacing. So the spacing between adjacent grooves, right? Given in the unit nanometers per groove. You have this, you're using the sine function here, and then you're thinking about the incident and diffraction angles of those rays. Then you can think about that relationship being equal to the wavelength of light that's actually going to be constructively diffracted here. And then this guy, I'm going to change and not use the variable m. I'm going to use, for consistency's sake, that bold small n as the order of diffraction. Okay, remember that this is an integer. If you are struggling to recall what I'm talking about with order of diffraction, remember if you have light that goes through a slit, as that light leaves that slit, it goes in lots of different directions. Okay, so if I have a screen back here, remember that I'll have constructive and destructive interference of those waves of light. And so I might have the intensity of the photons that are hitting my screen back here in a shape that sort of looks like this, where n equals 0 is right here. This is n equals -1, n equals -2, right, at these peak maxima. Okay. N plus 1, n plus 2. That's right. So this is coming from that constructive and destructive interference of those multiple waves that are passing through that slit. Okay, so order of diffraction. What else do I need to say here? In order for multiple beams to interfere constructively, right, we have to have multiple path lengths to vary by an order of n, by an order of interference with the bold n. And so, meaning that these multiple blazed angles are required in order to get that constructive interference that allows us to pull apart individual polychromatic light into individual wavelengths of light. Okay, great. I think that's all I'll say about the function of the grating. Oh, we're not, you can certainly do this activity if you like, but I won't discuss it here. I do want to talk about some characteristics of monochromators. So basically, we should talk about how good a monochromator is at separating wavelengths of light. And so let me draw a picture. For angular dispersion, it basically is getting at how big of a difference is there between your incident ray and your diffraction ray. So if here is normal, and here's my blaze angle, if my incident ray comes in here, okay, do I have my diffraction ray here, or here, or here, right? So if this is my incoming ray, is my angular dispersion poor, meaning that the diffracted ray is not that far away from the incident ray, or is it better that it's farther dispersed? So this is defined as the change in diffraction angle per unit wavelength as a direct measure of, and we use it as a direct measure of a grating's ability to have two different wavelengths leave its surface at different angles. So the ability for how well dispersed a polychromatic light will be in terms of its monochromatic components as it leaves the grating surface. So, of course, we can give an equation that describes this relationship. So d beta change, so the change in diffraction angle over the change in wavelength is equal to the order of interference, so bold n, over d, which is the length of the grating, multiplied by cosine beta. So remember that beta is the diffraction angle. Bold n is the order of diffraction. And d is the spacing between the grating, between the blazes on that grating. Okay, so angular dispersion is pretty useful. The better separated your wavelengths are, the easier it is to select them using your focusing mirror and your exit slit. So the linear dispersion is a measure of the distance at the exit slit over which a range of wavelengths are distributed. So given the exit slit and your, let's call it range of wavelengths, will it take up this much room or this much length? Right, that's what the linear dispersion is really getting at. And so to improve linear dispersion, right, you can increase the groove density, increase the order of diffraction. or increase the focal length. So it uses the unit of millimeter per nanometer. This is pretty straightforward, I think. So the linear dispersion is equal to the change in y, which is the change in distance across the focal plane. Across which an image can be broadcast. So, right, this idea of here's the slit, how wide is your actual image that's being broadcast? So that's d sub y over the range of wavelengths that you're looking at. So, how wide is a particular range of wavelengths? The change in that width is equal to the focal length multiplied by dr over d lambda. And in this case, we are thinking about the focal length from the focusing mirror. So think about that focusing mirror projecting an image, right, onto that exit slit. That's what we're talking about here. Change in with respect to change in wavelength, of course. This is useful, but less useful than reciprocal linear dispersion. So let's talk about what that looks like for a minute. So reciprocal linear dispersion, so this has an L on it, differentiated from the reciprocal. This is a parameter used to actually characterize instruments. So if you go to buy a monochromator, they'll tell you something about the reciprocal linear dispersion of that monochromator as a characteristic of its performance. So basically, it's equal to the number of wavelength intervals contained in each wavelength of interval against the focal plane. So instead of thinking how much wavelength change do you get in a particular distance, they're saying, well, that's exactly what they're saying, actually. So how equal to the number of wavelength intervals contained in each interval of distance across that focal plane. So reciprocal linear dispersion is exactly what it sounds like. So I have change in wavelength over the change in the range at the focal plane, the length of the range of the focal plane, equal to, I can do a quick substitution of that first equation in here to get n and f. Okay, so this is how you would relate the diffraction angle, the length of the Blaise grating, and then the focal length with the order of interference in order to calculate the characteristic reciprocal linear dispersion for your monochromator. Cool. Let's talk about slit width. So slit width is a really critical parameter that I think gets overlooked a lot when folks are optimizing instrumentation for use. So remember that the effective bandwidth for a monochromator, right, not for an interference filter that we talked about earlier, is the range of wavelengths that can exit the monochromator at a given wavelength setting. So remember that in the example that we gave of this monochromator, we had dichromatic light, right? 2 wavelengths of light. And if we wanted to separate them from one another, okay, so if I have this guy separate from this guy so that I have a single optical image of that wavelength here and a single optical image of that wavelength here at the exit, right? I want those two things to be separate enough so that I can distinguish them from one another, because of course detectors don't, common modern detectors don't actually measure the intensity of the energy from a photon. They just count when photons arrive, right? It's almost like a binary above a threshold sort of digital measurement that we talked about in week 1. And so this monochromator is how we are selecting a particular wavelength of light from another. It's the only way that we can make that discrimination. And so the exit slit width is really important so that we can say confidently that we only have a particular wavelength of light that's exiting that monochromator at once. And so think about the effective bandwidth of an exit slit as if, so as, let's say I had polychromatic light had 3 wavelengths. Okay, so I have 1, 2, and 3. If I want only 2 to make it through, I need to adjust the exit slit width so that the effective bandwidth of my exit slit would be equivalent to the width, actually half the width of my exit slit. Okay, so let's talk about what that looks like. If I have an optical image that is the exact size of my an optical image of a particular wavelength that is the exact size of my exit slit, the effect is that the bandwidth for that particular wavelength, right? So it goes from here to here, right? This is the base of it. Here's the point. Okay, and this is effective power, right? So I'm getting lots and lots of photons of this second wavelength coming right out the middle. That makes plenty of sense. And then as they exit, they're going to disperse, right, to some extent out to the side. This is an issue if you don't have enough separation between your wavelengths of interest. Okay, so bear with me as we sort of reduce the wavelength or reduce the exit slit width and look at the effect. So as I reduce the exit slit width, I can see that with this additional space here, now as I sort of move this image across, so if I move you can't see what I'm waving my hands, that's dumb. As I move this image across the exit slit, as I move, so as this guy gets sort of displaced to this spot right here, there's nothing coming through right here, and that gives me this dip, right? Where I can actually see the separation between these peak maxima, okay? Here I couldn't see any separation between those peak maxima. So if I reduce it even further, and as I make this displacement of this beam of interest, right, all of a sudden now there's really nothing coming through here because of this giant space in between these 2 wavelengths. And so I have much better resolution in my spectrum that are collected with this instrument. And so an example, benzene vapor. If I'm looking at the absorbance of benzene vapor, I have a really small bandwidth for my monochromator. I can see peak resolution that's really excellent. As I increase the exit slit bandwidth, the resolution of this spectrum goes down pretty significantly. And so if I were interested in something like identifying shoulders on peaks or noise above signal, this would be something that would be interesting to me, right, in this 0.5 nanometer bandwidth. If I didn't care about that, sure, fine, it doesn't matter. You can use a larger bandwidth, but the idea is that you're just losing detail in your spectrum. Okay, detectors. We got to talk about detectors. There are a couple of, don't worry, this is the last category. There are a couple of characteristics of detectors that are useful. And so we are going to talk about those. But before we do, remember that a detector is a transducer. So the purpose of this detector is to transduce the non-electrical energy into electrical energy so that we can quantify it, use it in a way that is useful to us in the lab. Okay, so as we think about the component detector that does this that's responsible for this process, there are a couple of characteristics that we want it to have. First of all, we want it to be responsive, right? So the responsivity as a function of wavelength is basically the signal output over the incident radiant power. So how good is it at seeing 2 photons and producing a current that is equivalent to 2 photons? So let me give you some definitions here. X I'm calling signal output. And B I'm giving incident radiant power. So it's almost like a ratio of efficiency. Okay. Hopefully that one makes sense. Another characteristic that's important is sensitivity. So I'm going to give that big Q, and that's as a function of wavelength. Again, it's really pretty simple. It's just the slope of the characteristic above, right? So with respect to the wavelength, so basically how sensitive is your detector? All right, so dynamic range. So over what number of detected photons do you have count fidelity? If you are using a detector that counts photons as they arrive at the detector surface, over what range of photon arrival rates does your detector actually have accurate counts? So if things are coming really, really fast, does it start missing photons that are coming at it just because it can't respond that quickly? Which is a nice dovetail into rise time. So rise time is an interesting concept. So over time, okay, how long does it actually take for your detector to say, from the arrival of a photon, for your detector to actually say, yes, it's there? And so we usually think about this from 10% of the original signal to 90% of the original signal. I'm actually going to zoom in here. So here's time. Nothing, nothing, nothing. Something happens, and now we've detected it. So again, we're going from 10% of the original signal to 90% of the original signal. How much time did it actually take for that to happen? So this time is rise time. How long did it take to get from 10 to 90% of total signal for a given event? So how quickly can it respond, basically, right? This is usually dictated by the electronics that are in your instrument, in your detector. And it's usually something on like the nanosecond scale. Okay. The next that I want to talk about is dark signal. So basically, if I were going to define it, I would call it the electrical signal of the transducer, the detector, in the absence of radiant power. So if I don't shine any light onto it, how noisy is it? Okay. These are all characteristics that are important as you're considering what kind of detector to use in your instrument. So ones that we will focus on today, photomultiplier tubes, phototubes by sort of default. We'll talk about thermocouples. No, we're going to talk about a Gallet. We're going to talk about charge transfer devices. So as we go in, there are 3 main categories as I sort of delineated here. So there are some that deal with photons and some that deal with thermal energy. And so photon detectors measure incident photon arrival rates, as I alluded to in my previous explanation, rather than the incident change in energy. Thermal detectors detect a change in temperature with incident radiation. And then multi-channel detectors are photon or thermal detector arrays. So when we talk about CCD cameras, this is an array configuration. Okay. All right, so let's talk about each. So photon detectors, an example is a phototube. This operates, of course, in the analog domain, data domain. And so basically it operates via the photoelectric effect. And so the way it works is you have an evacuated transparent envelope, right? Just basically a glass globe. You have a collection anode and a cathode. So here's your anode, right? Labeled with A. Here's your anode. Here's your cathode. And in general, you have what's actually happening here is you have incident radiation, right? Your photon is coming. Oh, no, not that direction. What am I doing? No. You have incident radiation. So your photons will, remember, a detector, the idea is you're going to take it from a non-electrical domain to an electrical domain. So you have the incident photon hitting your cathode. And when that happens, an electron will be ejected and collected at the anode. Okay, that's the idea. And so the point of the way that this works is you have the number of electrons that are ejected and collected at the anode to be proportional to the radiant power of that incoming radiation. This is a common detector in old UV-Vis instruments, like if you have a Spec 20. And this photosensitive cathode is made of all kinds of different materials, but something that's responsive to the incident radiation. The pro here is that you have a relatively cheap detector. The con is that you have some pretty significant dark current from thermally induced emission of electrons from the photosensitive cathode. So you've got some noise, which is not great. What you do want to make sure you're doing is holding the bias difference between your cathode and anode at pretty high voltage so that you are at a saturation range where any incident photon will actually produce a proportional current across those two electrodes as that electron moves across. All right, so that's a photon detector, pretty straightforward. Another kind of photon detector that it works off the exact same principle is called a photomultiplier tube. And so the difference here, right, phototube versus photomultiplier tube, is that we are amplifying the signal that we get at the end of this detector from the same amount of incident radiation. And so here we have dinodes, which provide a secondary electron emission on that photosensitive cathode again. Materials vary, but are generally alkali oxides, etc. We have very sensitive measurements here because we're getting that amplification of signal. So let me show you what I mean. So here are my dinodes, these blue sort of what look like lenses, but really they're just metal plates. I have incident radiation on my first photosensitive cathode. I'm holding all of these dinodes at an increasing voltage bias so that I have sort of control over the direction that these things go. So I have my incoming radiation. Remember that we have ejection of an electron from that photosensitive cathode material. When that happens, once I have that first ejection of an electron, so here I have one photon hitting, I'm going to eject 2 electrons. From this 2 electrons that were ejected, I'm going to have 4 that hit the next dynode, and from to the next I'll have 8. Right, and here I'll have 16. Here I'll have 32, and I won't do all 32, but you'll get the idea, right? I'm amplifying the signal from this single photon. I end up with 32, in this case, electrons that are coming here. This is a much bigger current that I can measure accurately using this detector. And so the idea here is that at the end of an actual PMT, you'll have 10 to the 6 or 10 to the 7 electrons produced for every one incident photon. This is a front-on PMT. The same thing exists. You could have a side-on PMT. This looks more like a little light bulb in your instrument, so it saves space. But again, you have an incident photon on our first photosensitive cathode. The release of 2 electrons here, which will come and be collected here in the form of 4 electrons, collected here in the form of 8 electrons, and you can sort of just draw the path, right? So this is just a more efficient use of space to accomplish the exact same mechanism in an instrument. All right, so these are great. They're really sensitive to in the UV vis range. They're really fast. They have fast rise times. The sensitivity is limited by dark current, just as it was for a photomultiplier tube. You have thermal emission in this case, which can be a significant source of noise. The other sort of delimiter here is that you are limited to low power radiation, right? You can't have too many photons that will be incident upon this detector at any one time, or you're going to saturate it and you're not going to have a very large dynamic range. Okay. Photodiodes are another example of photon detectors. So these are doped semiconductors, right? So silicon lattices with impurities in them. So you are again looking at a PN junction. So you're looking at electron pair holes. So basically the idea is that photons will produce electron hole pairs that will sweep through your device to produce a current or a voltage, depending on the bias that you're holding that junction at. And so the idea is that one incident photon gives one electron hole pair that can sweep through that silicon device. So let's draw a picture. Here's my P, here's my N, here's my depleted region, right where my impurities are. I have some sort of photon that is incident upon here. I will form an electron hole pair that is able to sweep across this detector to be converted into current. Very exciting, not super efficient. Relatively small dynamic range, right? Oh no, maybe I have not talked about that. Okay, so also because so I mentioned that these are not super efficient. Another way to think about this is, just as we used a amplification technique in a photomultiplier tube from the effect of a phototube, we can do sort of avalanche amplification in these diodes as well. So basically increasing the bias to get more than one electron hole pair for a single photon to be for a single incident photon. And so we call these avalanche photodiodes, or APDs. These are common these days. They're cheap. They used to be really expensive. They're cheap now, and they're much more sensitive than just a simple photodiode detector. And so if you're thinking about using photodiodes in an instrument, you're probably actually going to think about using an avalanche photodiode, just because of the increase in sensitivity, and really no significant increase in noise. Okay, I want to talk about one thermal detector that's common in IR instruments, and that is a Gallet detector. And so these sort of thermal detectors don't operate off of the photoelectric effect. Instead, heat detectors consist of small black bodies right? Remember, a black body is something that absorbs all of the incident radiation that's incident upon it, but is at thermal equilibrium with its surroundings. And so the idea that this material, this black body, absorbs the radiation, the effect is that you increase the temperature of that black body, and that's how we measure the incident radiation, right, is by measuring proportional change in temperature. And so when I'm talking about change in temperature, it's like really small, a few thousandths degree Kelvin. It's small. All right, so this particular detector that we're going to talk about is actually a pneumatic heat detector. So let's look at what it actually looks like. So I have a transmissive window. This is where my light will shine, okay? Attached to it, right, it encloses a gas-filled chamber. At the backside of my gas-filled chamber is my black body, right? Likely more like a gray body, but we'll assume black body here. On the back side of that black body, excuse me, there's a smaller compartment that is separated, right, into two parts via the distinction of this small membrane. So I'm going to label this as a membrane. So it's can be deformed in the face of increased pressure, right? Okay, so as this puppy heats up, as this black body heats up, right, the pressure in this first chamber increases and it presses this membrane into sort of a deformed shape back into the second detector. There are two lenses here in front of a photodiode that when this membrane deforms, all of a sudden the light from this photodiode is diffracted in a different way. And so you have a change in the photodiode optical readout of this detector. Okay. So the motion of the membrane produces a change in the signal on the photodiode. The idea here is that it's very sensitive. The con here is that it is very slow. So if you have a consistent signal, this is going to be a great for you. If you don't, this might not be the detector for your application. All right, the last kind of detector that we're going to talk about are multi-channel detectors. So these are, oh, hey, look at that, photodiode array. And I have also listed here a charge coupled device. So photodiode array are thousands of individual photosensitive elements, i.e. photodiodes. The entire spectrum can be measured simultaneously and continuously, which is exciting. It cannot match the sensitivity of a PMT. It can't match its signal to noise or its processing speed. So these are great, except if you need high sensitivity, low signal to noise, or a sort of dynamic measurement. Excuse me. So a charge coupled device is probably the more common multi-channel detector that you'll run into, but because it has the performance characteristics of a PMT, but allows for a larger range of wavelengths to be measured at once, which is exciting. So the idea is that you bin pixels when you use this for spectrometry. So you have an optical input, which is so your incident photon, which is these arrows here. It's going to hit this insulator, and charge will be stored under these metallic electrodes that act sort of as little shepherding gates. And so the idea is that this charge will be sort of ratcheted across this sort of assembly line of pixels in my array detector, and then it can be detected in register, which is exciting. So I'm gonna see if this works. There's a GIF that sort of shows how this, maybe? Yes, I wanna go there. Okay, so as I move the voltage on these gates, I'm moving the charge down this PDA, or sorry, down this array detector. So I'm applying a positive voltage, right, to each gate sort of in sequence to move and shepherd the charge down the array. So let me go back. So right down the array in this direction. Once it hits this spot, it's read in register. And so this is how we can sort of get such a wide optical image, basically, from the array detectors. Right, this charge comes from the electron hole pairs that are produced, the same way that they were in that photodiode detector example that I gave earlier. All right, last slide. We're making it. There are a couple of sources of noise in CCDs that are really, because CCDs are so prevalent, I think we should discuss these specifically. So one of them is shot noise. So this is also sometimes called photon noise. And basically, you're having random arrival of photons in time. So photons are arriving randomly. The next is dark noise. So this is thermally generated charge, which is not great. This is reduced dramatically if you cool your array detector using like liquid nitrogen. The next is readout noise. So the conversion of electron to voltage induces noise, right? So the registered readout on the side of that detector, you could induce some noise. So this is where we have conversion, noise in the conversion of electrons to voltage. The last kind is blooming, and this is really common. So this is the over illumination of individual pixels. Right, or buckets. If you want to think about that charge under a particular metal gate as a bucket of charge. So those individual pixels sometimes are over illuminated, and the effect is that the charge can spill over into another pixel, right where it shouldn't be, because there was no original incident radiation there. So over illumination results in blooming. It's pretty easy to see, but you should definitely keep an eye out for it in these experiments. Okay, I think I'm going to leave it here. I'll see you all next week.